My project is a compiler and interpreter for the TSTK language. The TSTK programming language is one that I designed, and it is a stack-based programming language designed to resemble assembly language. Now, a stack-based programming language is one in which the only data structure in the language is a stack, or in this case, a stack of integers. All operations in the language operate on the stack. So, for example, if we want to add two numbers, we take them off the stack and add them together, and then we push the result, which in this case the result of adding 4 and 5 is 9, back onto the stack. Every operation in TSTK works on a similar principle to this. The TSTK language itself looks like this. Comments begin with a hash sign here, and commands are just words. Integers present in the program are pushed onto a stack. So here, when we reach this line, 0 is pushed onto the stack. Here we push 1 onto the stack and add the top two numbers of the stack. There's many, about 20, operations that can be performed on the stack in the TSTK programming language. In addition to being able to push integers and perform operations on the stack, the TSTK language also supports labels. And basically what a label is a label that stores the address of the next operation. So in this case, loop stores the address of the operation to push 1. A reference pushes the address of a label onto a stack. So this is useful because when we jump, which is similar to go to and see, we need this address. So every command in TSTK has an address, with the first command being indexed at 0. So this would be at address 0. This would be at address 1. This would be at address 2. Note that labels do not get their own addresses. So references are actually just a number when the program is compiled. So loop is a label that references the address 2. So when you have this reference here, 2 is pushed onto a stack, and this jump statement says, aha, I will go to the instruction indexed at 2, or at the address 2. So the TSTK language supports quite a number of operations. Here's a list of them. We have your standard addition, subtraction, and multiplication and division operations, which simply take the first two elements off the stack and perform these operations. Dupe duplicates the top element of the stack. Jump takes an element off of the stack and interprets it as an address for an instruction. So back here, jump less than would pop 2 off the stack because that's what the value of loop is, and it would go to the instruction that has the address, which is the one right here. And then we have jump instructions that pop 3 elements off the stack and compares them for the first 2 for equality, inequality, or greater than or less than values, and jumps to the address if and only if that the inequality, the comparison is true. Get is slightly more complicated. It pops an element off the stack and interprets it as a value to get out of the stack that is that many levels deep. So, for example, if you have 3 get, it would get the element that is 3 places down from the top of the stack and push it onto the top of the stack. Set works similarly, except instead of getting that element, it sets it to another value. Pop simply pops the top element off the stack. P-push pushes the current position or the current address of the next instruction. Print, well, it prints the element on the top of the stack. cprint is like print, except it prints the ASCII character encoded by value. So, for example, if you have 56 on top of the stack, the letter, I believe, capital A would be printed. Maybe it's lowercase a, I can't remember. Read does, well, it basically reads an element from the input standard in and pushes it on top of the stack. Size pushes the current size of the stack onto the stack. Swap swaps the top 2 elements on the top of the stack. And finally, debug simply prints the entire stack onto the console. This is useful for debugging the stack, as its name implies. So, the T-Stack interpreter supports command line interpretation. So if we start it up, we can actually play around with it. So like I said, an integer, when T-Stack encounters an integer, it simply pushes that integer on top of the stack. So here we have 1, and then we push 2. Note that I'm using a certain notation here where the stack is represented as an array that goes out to the right. So you could push 3, 4, 5. And now if we execute a command like add, it will add 4 and 5 and push the result 9 on top of the stack. Now if we want, we could multiply the result, the top two elements on top of the stack, and you can see we get the correct result, 27. And then just to demonstrate that I/O works, we can print the result. Now, if we push 3, 4, and 5 back onto the stack, I can demonstrate the operation of get. So, get takes an element off the stack, in this case 2 here, pushing on 2 onto the stack and calling get, and counts down from the top of the stack, starting at 0, until it reaches that index. So here we start at 5, which is 0, we go to 4, 1, and 3, which is 2. And it takes that element and pushes it on to the top of the stack. And then we could say add 5 to that element. Now set, if we call set, we could say to set. Now set doesn't include any of its inputs when counting down from the top of the stack. Neither does get. So set takes 2 arguments. Here it's 8 and 2. Now 2 is the index it's looking for. So again it counts at 0, 1, 2. And it sets this element to 8. Like so. And finally, to demonstrate how a label works, we can have a label here, loop, which points to or stores the address of the next instruction. Here we're just printing 1. And then we can print 1. Next, I'll just store the address of loop on top of the stack. So in this case, the address is 17. If we start at 1, up here, counting at 0, we get 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So this is the 17th instruction. Now, if we jump, it will jump back to the 1 here. But if we do this, it'll push 1, print it, store the address of loop, and then jump back. So again, infinite loop where we print 1, as you can see here. So that's the basic usage of TSTK. Now, going back to the program I was just showing you, this program reads a number in, call it R, and counts up from 1 to that number. So here we have 0, we push 0 onto the stack, and we have R on the stack. So that's something like this. We have a stack as it R, comma, n equaling 0. Just refer to the top element as n for now. And then we go to loop, which points to this 1, and we push 1 and add it. So here we get R, comma, n plus 1. And then we duplicate and print. So this just prints the value of n plus 1, which in the first loop is just 1. Now we duplicate it again, and we get R, comma, n, comma, n. Now if we execute to get, again counting down from 0, we go 0, 1, 2. So we push R on top of the stack. And then we jump back to loop if n is less than R. So if n is less than R, go to loop. And back, we go back to loop, and at this point, we have R and N on the top of the stack. Because remember, the jump less than command will pop these two elements off the stack. And so we continue like that, and it adds 1 each time and prints the result until n is greater than or equal to R. So to demonstrate that this works, I'll run it with the interpreter. So so if we run examples /count, it asks us to enter a number, so let's enter 9, and indeed it counts up from 1 to 9. Now, one interesting thing about my TSTK implementation is that the interpreter also allows you to enter a debug mode when executing a script. So in debug mode, we can execute each line one at a time. So first we read and number n on top to the top of the stack. I'm going to enter 2 because if we enter 9, the script will be running all day. It'll be a pain to go through every command. So it pushes 2 on the stack, then 0, and then 1, which again is this 1 right here, and it adds the top 2 numbers together, and you get 1. Now it duplicates that top number, it prints it, then it duplicates it again, pushes 2, gets that element, which in this case is 2, 0, 1, 2, pushes the address of @loop, which is again 2, and jumps there if 1 is indeed less than 2, which is. So we go back to the, again, 1 right here. We push it, we add it, we duplicate, we print it, we duplicate again, get the second element down, which is, again, 2, store the address of loop, and jump if 2 is less than 2, which is not, so we don't jump, and the program ends. So as you can see, we printed 1, or 2, and 1, so we've been counting up from 1 to 2, which is what we wanted to do. The last feature of the TSTK compiler that we should go over is the compiler itself. So, invoking a compiler is rather simple. Just pass in the -c flag for compilation and specify the output. So here, we're compiling the count TSTK program to a C program. Now, all TSTK programs rely on a runtime library. So before we can compile the count.c file, we have to compile the runtime. So if we do that, now, if we compile a count.c file, my bad. We can link it with the runtime and get our binary file. Now if we run it, oops, misspelled that. If we run it, you see it behaves exactly as if it was interpreted. So that's the compiler. Now the actual compiled C code is pretty ugly, so I won't go into that in depth. Yeah. So, yeah, this is the compiled C code for the count program. Now, to finish off, I'd like to discuss the main pipeline for the TSTK program, compiler and interpreter. So basically, all programs begin as source code. The next phase of compilation or interpretation is to pass it through a lexical analyzer. A lexical analyzer breaks the code up into tokens, which are basically just in-memory representations of the words here. So, yeah, 0 would be a token, loop would be a token, yeah, print, whatever, they're all tokens. So the next phase is to do label reference conversion, which basically removes all the labels and replaces the references with numbers, the addresses of the instructions that the labels point to. In this part of the compiler, we use a map, and I use a map, to basically build up a table that maps label names to the addresses they point to. And then we do another loop over the tokens to basically remove all the labels and replace the references by looking up the addresses in the tables. So after that, we basically just get a bunch of instructions, TSTK instructions. So from here on out, there's two different paths we could take. We could either pass the instructions to the compiler backend, which converts it to C source code, or we could pass it to the interpreter, which interprets the code and executes it. If we're executing a debugger, then we basically execute a line and then go back around, execute another line. Just a loop where we execute each instruction one at a time. If we're in the console, then we read more source code from standard in, and then repeat the process. So, pass it to a Lexical Analyzer, convert all labels and references, and pass it back to the interpreter. Each of these phases has an O of n time complexity, which should be obvious. It just to break the code up into tokens, we just read it left to right like most humans would. I mean, the computer does that. And label reference conversion, we do two passes over the tokens, one to construct the table and another to replace all the references and remove the tokens. And then the compiler again just does one loop, converting each instructions straight into the appropriate C code. And the interpreter, it only takes it takes a constant time to interpret each instruction, so depending on how big your source code is, it'll take longer. So everything, each pass has an O of n time complexity. So that's basically how TSTK works. And thank you for watching. Good night.